Hi, welcome back. We're talking about using the continuous time Fourier series properties to calculate the continuous time Fourier series. And I've got an example here that we're trying to determine the CTFS of g of t, this square wave here. Now, in a previous video, we calculated the Fourier series coefficients of x of t, this centered square wave with a pulse width of 2t1 and a period of t, and we found that its Fourier series coefficients were given by these expressions here. So now we see that x of t and g of t might be related. Can we use the result from x of t to and apply it to g of t to get its Fourier series coefficients? So if you look at x of t, it's got a high value 1 for 2t1 units of time, t1 to the left and t1 to the right. So we might say that its pulse width is equal to 2t1. Right, now we look at the given waveform g of t, and its high value is 1/2, but its high value is for 2 units of time. So in order to compare apples with apples, we have to pick these parameters correctly, and we see then that t1 is equal to 1 unit of time. Okay, and then the second parameter was the period t, and I look at g of t and I see how many units does it take to repeat, and it looks like it takes 4 units to repeat. So here are my parameters for the square wave. When we calculated x of t, we left those parameters as variables, but now I can lock them down with my given example. So now let's be concrete here. X of t has Fourier series coefficients given by 2t1 over t, well that's 1/2, when k equals 0, and then we have the sine of, well, if the period is 4, that implies that omega 0 is 2 pi over 4, which is pi over 2. So this is the sine of k pi over 2, right, and then over k pi, when k is not equal to 0. All right, so those are the Fourier series coefficients of x of t with these given parameters. Now, how is x related to g? Well, if we take x of t, notice we have to delay it by 1 unit. Why 1 unit? Because the center of that pulse there happens at t equals 1, where the center of x of t happens at 0, right? So if we take x of t and we delay it by 1 unit, now, imagine this square wave getting shifted to the right by 1 unit, and then we also have to shift it down by 1/2. So we're going to subtract 1/2 from everything, so that the high level is not 1 anymore, it's 1/2, and the low level is not 0 anymore, it's negative 1/2. So this is how g is related to x. G of t is x of t minus 1 minus 1/2. Now, we're going to start to apply those properties. And we're going to just kind of keep track of a list of the properties that we apply. So we're going to apply linearity first. So what does that do for us? Well, that allows us to take the Fourier series of each piece separately, right? We have 2 terms here, x of t minus 1 and then minus 1/2. Linearity allows us to look at each piece separately, much in the way you would take a derivative or take an integral. Okay, so let's look at the first piece, x of t minus 1. Well, we're going to use the Timeshift property. I'm just going to write by linearity piece by piece, just to remind us how we're using it. Then we're going to use the Timeshift property. And remember, the Timeshift property says that x of t minus 1, or I guess we'll write it as x of t minus t0, has Fourier series coefficients ak, so the originals, times e to the minus j k omega 0 t0. Okay, so I'm going to apply the Timeshift property, and I'm shifting by 1 unit of time. So I'm going to plug 1 in for t0, and so this becomes ak e to the minus j k, and we've already said omega 0 is pi over 2. Okay, so my Timeshift property says I have to take all of the Fourier series coefficients of x and multiply them by e to the minus jk pi over 2. Okay, so that's the Fourier series then of x of t minus 1. Now, what about the 1/2? Well, let's call the 1/2 bk's. Let's have the 1/2 be have Fourier series coefficients denoted by bk because we already used ak for x of t. So what about 1/2? We've never talked about the Fourier series coefficients of a constant. Well, a constant does not oscillate, so it should not surprise you that it has 0 coefficients for the harmonics, and its dc term is actually just the constant, right? So this is saying 1/2 has the constant term 1/2, the k equals 0 term, and it has no oscillations, it has no harmonics. Okay, so now we're ready to put all of this together, and we see that g of t then would have the Fourier series coefficients, and then it's going to be piecewise. So for k equals 0, then we would have so k equals 0 is 1/2 times, and then this thing evaluated at 0, e to the 0 is 1. So we would have 1/2, right? The k equals 0 term is 1/2 times e to the 0, which is 1, and then minus 1/2 because of this minus 1/2. So we get 0 for k equals 0. And then for k not equal to 0, we would have this thing, ak, multiplied by e to the minus jk pi over 2, and then minus 0. So we would just have, we'd just write it like this, e to the minus jk pi over 2 sine of k pi over 2 over k pi for k not equal to 0. Okay, and those are the Fourier series coefficients. That's it. Now let's try to understand what our answer is. So again, before we get into the intuition of our answer, I just want to say that's the answer. Okay, so if you can stop there. But let's continue on. First of all, we're saying that it's A0 has a value of 0. That means the average value should be 0. So let's look at our wave g of t. Is its average value 0? Well, yeah. Half the time it's at 1/2. The other time, half the time it's at minus 1/2. So yes, it has a 0 average value. That corresponds to A0. That looks good. Now, what does this thing tell us, this k not equals to 0? Well, remember, we're saying that g of t is a sum of a bunch of oscillations, a bunch of harmonics. So first of all, notice that when k is even, we would have the sign of a multiple times pi, right? When k is 2, this would be the sign of pi. When k is 4, this would be the sign of 2 pi, 3 pi, and so on. And so for the even harmonics are 0. So the square wave only has odd harmonics, and if you're into music, a synthesized square wave, musicians always describe this as sounding like a hollow sound, and the reason it's hollow is because it's missing the even harmonics. Now, for the odd harmonics, let's just consider A1, for example. So if I plug in 1 to k, then I would have e to the minus j pi over 2 times the sine of pi over 2 over pi, right? So what is this? Well, e to the minus j pi over 2, that is minus j. Think about the complex plane, vectors and so forth. Sine of pi over 2, that's 1. And so this is what we get. And we can rewrite that as 1 over j pi. Or actually, but I'm gonna keep it the way it is. And let's just look at A3, just so we have two things that we can compare. A3, we would plug in 3 for k. So this would be 3 pi over 2 sine of 3 pi over 2 over pi, over 3 pi, excuse me. And so e to the minus j 3 pi over 2, that's equal to j. Think about your complex plane. Sine of 3 pi over 2 is negative 1, actually. and then we have 3 pi there, and so this becomes negative j over 3 pi, actually. So that's interesting. Now, what does this mean? Well, this guy, A1, has a magnitude, so the magnitude of this complex number is 1 over pi, and the phase of A1, the phase of this thing, minus j means to go down 90 degrees, or minus pi over 2. So the phase of that thing is minus pi over 2, and similarly over here, the magnitude of A3 is 1 over 3 pi, and the phase of A3 is also negative pi over 2. So what this means is that the first harmonic, the thing that's vibrating at a rate of pi over 2, has an amplitude of 1 over pi and a phase of negative pi over 2. And the third harmonic, which would be 3 times pi over 2, has a magnitude of 1 over 3 pi, or an amplitude, and a phase of negative pi over 2. So if you take those two waveforms and you add them together, right, you start to get something that resembles a square wave. And we wouldn't stop there, of course. We would add A5, and we would add A7, and we would continue on in that manner. Okay, so stay tuned. We'll have some more videos on how to use the CTFS properties.